Okay, so last time we talked about torque, and just to recall that torque is going to be your displacement cross force applied. And now what we're going to do is we're going to link torque to our angular acceleration that we picked up in the previous unit or the previous section. And so let's suppose first, let's just think about a point mass. So mass 1. And so we have this mass and we're applying a constant force to it such that it rotates in the XY plane about the Z axis. And so our rotation again is in the XY plane, but you can see if we follow the right hand rule, if we cross R here with F, then we'll get a torque which points up along the Z axis. That's following the right hand rule. And so what we want to do is we want to think about the acceleration of this mass. And so to derive this, we'll start with our familiar net force is going to be mass times acceleration. And so the net force acting on this is just going to be this tangential force. So we'll just call it a force. And then we have our mass times acceleration. This acceleration, though, is linear. That's the tangential acceleration. And so what we really want to get to is angular acceleration. And so if you remember, you know what, let's go ahead and put a T there just to clarify. So our tangential force creates a tangential acceleration. But remember that we can go from linear into angular by multiplying by R. So we get that the force tangential causes a angular acceleration of angular times R. Okay. Now what we can do, since this is at 90 degrees to the R, is let's go ahead and multiply everything by another R. And the reason for that is, well, you'll see. So we get M. I'm going to put the R's out front, and it would be R times acceleration. So what I did is I just multiplied each side by R. And that's fine, as long as you do the same thing on both sides. Now, since it's perpendicular, the tangent force is perpendicular to the radius, then the cross product is just going to be of the cross product of the torque would just be F times R, because that's cosine 90, which is 1. So we can see that this right here is torque. And then on the other side, we're going to get mr squared times the angular acceleration. Okay, so you should recognize this. This is the inertia of a point mass. So if I had a whole bunch of them, I could sum them up. Or if this were a solid object, like a rod or something, well, then it's just the inertia. And if I have multiple forces, well, maybe I can just generalize this to the net torque is going to be the rotational inertia times the angular acceleration. And this is true. So what we have is we have the analogy of force into torque, mass into rotational inertia, and linear acceleration into angular acceleration. So this is Newton's second law applied for rotational motion. On your equation sheet, it's written in let me make sure. Yeah, it's written in terms of acceleration, just like we did last year or the year before, whenever. Angular acceleration is defined as the net torque divided by the rotational inertia. Let me drag over your equation sheet. So it's right here. So you see the definition of torque followed by Newton's second law for rotation, and then our definition of angular. So that's basically it to tie it together, just knowing kind of where it comes from. So I'll do a few examples, and then you'll have a practice set. Okay, I think I'm just going to go through one example, but I'm gonna expand on it and stuff, so it'll end up being several. So let's just say that we have a disk, a solid disk, connected to some axle that goes right through the center. So we get something like that. So it's free to rotate about the center. And then we have a rope or something that's tied around, and we're going to pull with a force of 8 newtons. It has a 0.1 meter diameter. And so some questions we can answer are like, what's going to be the acceleration, the angular acceleration of this block? How fast is it going after a certain amount of time? And then we'll come back and see what it's going to take to stop it. So let's first figure out the angular acceleration. So using Newton's second, angular acceleration is going to be the net torque divided by the rotational inertia. The rotational inertia for a disk is going to be 1/2. So the inertia for this disk is going to be 1/2 mr squared. Okay, so the torque. The torque would be our force cross distance, or distance cross force. I guess I keep saying it backwards. But it's perpendicular to the r. So it's just going to be the r times the force. And then on the bottom, we're going to get the rotational inertia. So 1/2 mr squared. And then we can do some simplification here. I'm going to work sideways because I don't want to run out of room. These r's are the same. It's the radius, so that cancels one of those. And so then we can put the 2 up top. So we get 2 times the force divided by the mass times the radius. So we get an angular acceleration. It's going to be 2 times 8 divided by the mass. I didn't put a mass. I don't know. 20 kilograms. Sure. So 20 times 0.1. And we get, that's 16 divided by 8. I'm sorry. The whole thing, that's 2. The whole thing is 8. Sorry. I was trying to simplify. I'd already calculated it. That's 16 divided by 2. What units go on this thing? Well, it's angular acceleration, so that's radians per second squared. Our angular acceleration. Okay, so what can we do with this? Well, we could say like, well, how fast is it going? What's the angular velocity after, say, 10 seconds? So that would be our initial plus our angular times t. We assume the initial is 0, so my final velocity is going to be 8 times 10 seconds. So we get 80 radians per second. Okay, so now after 10 seconds, this thing is spinning at 8 and we drop the force. So we remove the force. Now the question is like what force of friction? So we have like a, I don't know, say a friction block, something like this. That's how your brakes on a bicycle work. So we're going to push this against it and it's going to create kinetic friction. What's that force required to stop it? Let's say stop it in a time of, I don't know, 3 seconds. Okay, to stop. So what we need to do is we need to figure out, we want to know the kinetic friction. So what we can do is we need to figure out the acceleration that we need. So the acceleration, let me do this. We're going to use this kinematics. So my final now is going to be 0, and my initial is going to become this final here. So that's going to go there, plus the acceleration times t. So this one's 0. So we get negative omega is the acceleration times time. So we divide that by time. And that's my my initial velocity. So we put 80 in there. So we get negative 80 divided by 3 is equal to the acceleration. And that is 26.67. So we're going to get an acceleration. We need an acceleration of negative 26.67 radians per second squared. in order to stop this thing within 3 seconds. Okay, so now we can figure out the torque that's going to be applied. So we're assuming that the torque is going to be applied. This thing is rotating by it, so the torque is opposite. It's going to work this way because it's kinetic. Rearranging this, we get the net torque is equal to the inertia times the angular acceleration. And the only torque acting on it is the kinetic friction. And that's going to be 1/2 mr squared times the angular acceleration of negative 26.67 from before. So we get a kinetic frictional force of 1/2 of 20 times 0.1 squared times negative 26.67. Let me calculate that real quick. I messed up here. I messed up going here. I did the net force. This should actually read your kinetic friction times R. That's torque. And then it's all the same, 1/2, blah, 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 blah. Let me just write it out. mr squared times the angular acceleration. So we can see this R is going to cancel one of these. So your kinetic friction is going to be 1/2 mr times the acceleration. Doing that, you're going to end up with 26.67, which happens to be our acceleration. So you get a net force of 26.67 is going to be your kinetic friction force. And that has to do with, it's going to be with the numbers that we chose, why it matches. That's not always true. Anyway, this is, I was just trying to show you, for these types of problems, you're usually going to have to go back and forth from kinematics into dynamics. So you'll use this along with our kinematic equations that we picked up in the last unit, like this one, and then the angular position and such. What I recommend is when you do it, a lot of times you'll see like RPM, immediately get that into radians per second before you do anything. Or anything like that. Anything that's on the standard units, do all your conversions first before you start them. But that's it.